Hello, viewers. Welcome to the Cyber Physical Control System course Module 2, Industrial Process Techniques and Instrumentation. So, in this video series, we will explore the fundamental principles of industrial process control system, which is used in modern manufacturing and automation industries. We will begin by understanding the operation of open loop control system, then followed by closed loop control systems, and the behavior process of the process variable and the role of the controllers in maintaining system stability. We will then study various control modules, including on-off, proportional, integral, derivative control, along with the advanced control techniques such as cascade, feed-forward, ratio control, and finally we'll examine the industrial controllers and the instrumentation, and which will enable the precise monitoring and control of the industrial process. By the end of this course module, you will gain a comprehensive understanding of process control strategies and then practical applications in industrial automation. In industrial automation, the primary objective of any control system is to maintain one or more process variable such as temperature maybe or pressure maybe or flow rate level or motor speed at a desired value. But to achieve this, the industry use the control system that continuously monitor and regulate these variables depending on the method of operation. So these control systems are broadly classified into two categories. One is the open loop control system and another one is the closed loop control system. So in this session, we'll understand the working principles, characteristics, advantages, applications of both control systems then. So first, let us look at this open loop control system. The process control operations are performed automatically by either open loop or closed loop system. If the process is controlled only by the set point commands without any feedback signals, the system is preferred as open loop. The open loop control is used in the applications where the simple process or performed timing functions are often the key factors that is used to control the operations. So there are some examples for the open loop process machines. That is the cafeteria dishwashers, commercially laundry machines, and printed circuit board burn-in chambers. So this equipment run through a series of timed cycles which are activated by controller devices such as relay ladder logic hardware, sequential drum controllers, programmable controllers, or computers. So the advantage of this open loop system is that they are relatively inexpensive, and the main drawback is that without a feedback loop, there are no control capabilities to make the corrections if the process deviates from its required value. So let us see one of the examples from the open loop systems. So a tank that supplies your water for an irrigation system, that can be used to illustrate the open loop system that has been taken for the example on this part. So this diagram shows a system composed of a storage tank, a inlet pipe, and with a manual control valve and an outlet pipe. A continuous flow of water from the natural spring, which enters the tank at the inlet, and the water flows from the outlet pipe to the irrigation system. The process variable that is maintained in the tank is the water level. Ideally, the manual flow control valve setting and the size of the outlet pipe are exactly the same. When this occurs, the water level in the tank remains the same. Therefore, the process reaches a steady state condition or it is said to be balanced. But the problem on this that if there is any change or any disturbance that happens, that will upset the balance condition. For example, you may take a rainfall that may occur, so which causes a additional water that may enter the storage tank from the top. Since there is more water entering the tank than the existing one, the water level obviously will rise. So this condition is not corrected, then the water tank will eventually overflow. Then excessive evaporation will also the one of that point to get unbalanced condition. So if it occurs over a prolonged period of time, the water level in the tank may become unacceptable low. So we need a human operator who periodically inspects the tank that can change the control valve setting to compensate for these disturbances. For an example of a manually operated open loop system is the speed of the car, of course. So that will be controlled by the driver. So the driver adjusts the throttle to maintain a highway speed when going uphill, downhill, or on the level of terrain. Now let us see example for the closed loop control system. A closed loop automatic control systems which are most expensive than the open loop systems. With the addition of a feedback loop, they become self-regulating. The diagram which is used to illustrate the operation of a temperature pressure process closed loop control system is taken and which is shown, and it shows a heat exchanger which is used to heat a liquid to a temperature of 100 degree Fahrenheit. Your source of steam supplies the thermal energy to the exchanger. The amount of steam that passes through a control valve determines the temperature at which the liquid is heated. Primary element is the sensor, and which is used to detect the condition of the controlled variable, which is the temperature of the liquid leaving the exchanger. The sensor output, which is called the measured variable, is continued by a transducer or transmitter into a standard signal before it is sent to the controller. The controller then converts the feedback signal to its set point. Suppose if there is a error signal is developed, if there is a difference, the controller uses the error signal to make the computations to determine which type of control signals to be produced at this output. The control signal is then finally sent to the control element, obviously, which is the control valve. Then this valve varies the steam flow into the exchanger. Now the steam is then manipulated variable that causes a change in the control variable. These actions of measuring, comparing, computing, and correcting, and which will go on continuously. And another one example here also you can see it that there are many situations in industry where the open loop system is adequate. However, some manufacturing applications require continuous monitoring and self-correcting actions of the operation for longer periods of the time without interruption. The automatic closed loop configuration performs the self-correcting function continuously, and this automatic system employs the feedback loop to keep track of how closely the system is doing the job, and it was commanded to do so. The reservoir system can also be used to illustrate the closed loop operation. To perform automatic control, the system is modified by replacing the manually controlled valve with an adjustable valve commanded to do so. So if the level of water in the tank goes up, the float is pushed upward. If the level goes down, the float moves downward. The float is connected to the inlet valve by a mechanical leakage. You can see it in the figure. As the water level rises, the float moves upward, pushing the lever and closing the valve, thus reducing the water flow into the tank. Suppose if the water level lowers, then the float moves downward, pulling the lever and opening the valve, thus allowing more water into the tank. To adjust for your desired level of the water in the tank, the float is moving upward or downward direction. The most automated managing process or closed loop control. So these systems that have a self-regulation capability and which are designed to produce continuous balancer. And next very important topic on this module 2 is that process behavior. So the primary objective of that process control is to cause a controlled variable to remain at a constant value or near some desired set point. The time variable refers to the fact that the element rises when an influence to which it is exposed causes the variable to change. So a change can happen when only one of the following condition occurs. First one is that a disturbance appears or the load demands that may vary at set points are adjusted. When a change that does occur, the objective of the process control system is to return the control variable to the set point as quick as possible. So here the two figures that has been given for an examples. So you can see the first figure where the flow of liquid through a pipe system is the process. The fluid flow rate leaving the valve is the control variable. The position at which the valve is set is considered as the set point. The flow rate governed by the position of the flow restrictor inside the valve is a manipulated variable. The demand for fluid downstream from the valve is the load, and the variance in the upstream pressure is considered the disturbance. Now you look into that figure 2, where how a set point change or disturbances or a load variance affect the control variable is shown. Let us consider the flow. The control variable is plotted on top of the measured device such as the strip chart recorder. Let us consider at a time 1, the flow rate increases when the valve position is open wider, while the upstream pressure remains constant. But at time 2, with the valve position unchanged, the flow rate decreases because the upstream pressures drops. So the flow rate would decrease in smaller fashion if the demand for the fluid decreased downstream while the upstream pressure and the valve position remain constant. The controller operation is also the element for the closed loop system that process the information needed to perform the decision making function without the intervention of the human being. So the input that is applied to the controller is an error signal, which is proportional to the difference between the desired set point and the feedback signal. The controller then calculates the changes which is needed in the control variable to compensate for disturbances that upset the process that causes the change in the set point. Now the controller responds to these changes by producing an output signal that drives the actuator to alter the control variable until the error signal is reduced to 0 or to the baseline. Now, the controller may be as simple as a spring balanced mechanical lever or a complicated as a computer, and it may control one process or it can also control a several processes simultaneously. And moreover, the controller can also operate as an analog type or digital type, or which can also be the combination of both here. So in the module 1, we have seen a different modes of operations, especially the on-off control method. Besides, there are several mode of operation is also available, such as proportional integral, the proportional integral derivative method. So all these four methods of control response to the error signal, they differ in the speed, accuracy with which they eliminate the error between the set point and the control variable. So the control modes are called as on-off proportional integral derivative, where the on-off mode of operation that we have discussed very wisely in the module 1. So viewers, if you like to know about more detail about the on-off control mode of operation, please you can view the module 1 video lectures and there you can learn about it. So in this video module, we go for looking into that deep learning about proportional integral and derivative modes of operations. So now first we'll look into the proportional mode. A proportional controller produces an output signal with a magnitude that is proportional to the size of the error signal that is correcting. So the error signal is the difference between the measured variable and the set point that we know already. The set point is also called as the desired value. So a smaller error will cause the output to change by a smaller amount. Similarly, a large error will cause a large output change. The output of the proportional controller moves the final control element to a definite position to attain the desired value of the control variable. So this proportional action that can be accomplished in two different ways. One of the ways that time proportioning method and another is the amplitude proportional method. So the time proportioning method is a method in which the output of the controller is continuously fully switched on or it is fully switched off. The average voltage produced is varied by changing the ratio of signal on to signal off. The ratio produced by the controller is determined by how much the measured variable differs from the set point. Yes, of course. If the measured variable equals the set point, then the output on to off ratio obviously 1:1. Then you can see it in the figure A. And similarly, if the ratio indicates that on time and the off time are same, if the measured variable is below the set point, then the on time will be longer than the off time. That you can see it in the figure B. So if the ratio increases as the error signal increases, then producing the higher average output voltage. When the measured variable is above the set point, obviously the on time will be shorter than that of the off time. That you can see it on the figure C. Amplitude proportional. So in the amplitude proportional method, the most common technique used to produce the proportional signal is the amplitude, or we call it the magnitude. So the magnitude of the signal is proportional to the size of the error signal. The analog signal produced by the controller is either a voltage variable or the variable current. The controller is also having the capability of amplifying the amount at which the output changes in proportional to the change applied to its input. There are two ways to refer the amplification of a proportional controller. One is the proportional gain and another one is the proportional band. Let us see one by one what is my proportional gain. It is nothing but the ratio of change in output voltage to the change in input are described mathematically by using the formula. Meanwhile, the proportional band is also something different that we'll see it after looking into one of the examples for this. The float mechanism that regulates the level of fluid in the tank is used in the figure to show the concept of the proportional gain. Now let us see. Referring to the gain formula, the liquid level represents the input and the amount of fluid that flows through the inlet flow valve is the output. Suppose if the load demand is increased by increasing the opening of the drain valve, the result is that the liquid level drops by 5%. To prevent the level from the dropping any further, the flow valve opens by 5% and increases the inlet flow 5%. According to the formula, the gain is 1. So we come with the proportional gain is equal to 5% the output change to the 5% input gain. Obviously, we get that ratio becomes 1. Now we look in this the proportional band. So the width of the proportional band determines how much the controlled variable change is required to cause a given amount of movement by the final control element. So the gain and the proportional band are two different ways by which the adjustable amplification setting is made to the controller. Both values determine the magnitude at which the output changes in response to an input change. The next one is the integral mode. When the set point valve position in the figure is exactly a 50% of its full flow rate capacity. Suppose if the load change occurs from an increase of that output flow through the drain pipe as the level drops, the float mechanism causes the opening of the inflow valve to increase it. When the inflow equals the new outflow valve, the system stabilizes. However, the level is below the set point as shown by the diagram. If there is an error or if this is the error, a constant difference between the set point and the control variable is called as offset. Some system cannot tolerate this effect because they require that the control variable return to its original value. To eliminate the offset, a integral function is added with the proportional mode to the controller. To perform the integral action, the controller senses that there is a difference between set point and the controlled variable. As long as there is an error exists, then the integral mode continuously causes the controller to adjust its output until the offset returns to its zero. It performs this function by either adding or subtracting from the controller output. The longer the error exists, the greater the integral becomes. So that is the objective of this integral mode. So here you can see the graphs. So the graph in the figure shows the functions of the proportional and integral actions in response to the gradual load changes with the duration of 1 minute. During the first minute, you can see in the graph, the proportional output increases as the load changes. At 1 minute, the load stops changing and the proportional output stops increasing. However, there is an offset and the integral mode continues to increase the amplitude of the controller output. So this result is that the final control element is adjusted until the control variable returns to its zero position. So the advantage of the integral mode is that the integral mode is used in process applications where the load varies slowly but by a larger amount. So the magnitude of integral would be large if the proportional gain is smaller than when the proportional gain is larger. So next we are going to look into this derivative mode. So integral mode we have seen. Now we check with that derivative mode. If the set point or load changes suddenly, the control variable will deviate from the set point and that will create an error. This one obviously we know it, but the higher the initial rate of change, further that control variable is apt to move away from the set point. In some process application, this situation is undesirable. So if the proportional gain is increased to minimize this condition, the control variable will likely to overshoot and that will oscillate. So this situation may not be acceptable because a product could be ruined if the tolerance of this condition is exceeded during the overshoot or the peak of each oscillation. Instead of increasing the proportional gain to reduce the error signal, the derivative mode of controller is used. So that's the biggest advantage of this one. So you can see this figure shows how derivative mode reacts to the load change. So the top portion of the graph shows the error signal and the bottom portion of the figure shows the proportional and the derivative outputs of the controller. So during the first half of the time period A, the load change causes the process error to increase by almost 15%. The proportional mode with the gain of 1 causes the control output to increase from 50% to almost 65%. So that you can see the point B. The derivative mode shown by curve D that adds a proportional signal and causes the controller output to increase from 50 to 90%. So this result is the final element that makes a large change, which causes a quick system response, but that prevents the control variable from deviating any further from the set point. In the middle of this time period A, the rate that the error signal is increasing begins to drop off and the derivative output begins to decrease. At the end of this period A, the error signal stops changing and the derivative output goes to 0. At the beginning of this time period B, the error signal starts returning to 0 and the proportional output reduces by the same amount. The derivative action responds to the reduction of this error signal by reversing its polarity as shown in the figure B line. You can see it. So during the first half of the time period B, the amplitude of the derivative increases as it is subtracted from the proportional output. So this results decrease in the controller output provides a braking action as the control variable approaches to the set point. So during the second half period of the point B, the amplitude of the derivative output decreases and the amount at which it is subtracts from the proportional output diminishes. So this action minimizes the overshoot, a condition where the control variable goes past to the set point value. At the beginning of the time period C, the error stabilizes and the derivative signal goes to 0 and the proportional output is small constant value which is unable to overcome this offset. So the limitation of this derivative mode is that it is never used alone, but in combination with the proportional and the proportional plus integral can be used. So this action is unable to remove the offset present in that proportional control. So this offset is a steady state error, which means that it is a constant. Therefore, since there is no rate of change that occurs, the derivative action produced is zero. The derivative control is also unsuitable for the system that are exposed to noisy environment because even there's a small noise occurs in a high frequency components that are amplified by the derivative action and this amplified signal will appear at the controller output that may cause unwanted changes by the final control element. So the benefit of this derivative mode in two different types of process application. So those that have a large and rapid load changes in slow response system that may be used. Another one is that in which the systems which are subject to frequent startups such as batch process. Batch process is mostly used in that sorry that can be used in that phase of restaurants. So here we can see that differences between proportional plus integral, then plus derivative, then integral derivative methods. So the proportional method that provides a gain and that is application used for the small set points and small load changes. A proportional plus integral method that is used to eliminate the offset value for the large and slow set point or the load changes. Proposed plus in derivative method, the function is used to speed up the responses and minimize the overshoot. And that can be used for the applications such as the sudden set point or quick load changes in the slow response system. Proposed integral derivative PID controller that may be used to speed up the response and minimize the overshoot and eliminate the offset. And that may be widely used for the applications such as large and sudden set point and load changes in a slow response systems. Now we'll see into the advanced control techniques. So nearly all the control systems are based on the principles of feedback control. Yes, the system of the control system is to maintain the control variable or to close to the very set point as possible. So by incorporating the characteristics of all these three PAD modes into a single loop, the degree of control may be adequate for most of the situation. However, some complex manufacturing applications are often require the most advanced controller to ensure the most precise control of the process. There are four of these techniques that are frequently used. One is the cascade control, feed forward control, ratio control, and last one is the adaptive control. So the cascade and the feed forward control techniques provide the faster and tighter response than the PID control because they detect the disturbances when they occur and begin correction early to overcome the effect of the dead time and the process time constant. Bef- Besides, the ratio and adaptive control techniques are used to accommodate the unique success or the unique process and the measurement situations. Now let us see one by one those advanced control system. So now firstly let us see the cascade control. So here we have a inner loop which monitors the manipulated variable, that is nothing but the steam pressure, and that is referred as the secondary feedback loop. The outer loop which monitors the control variable, which is a liquid variable, liquid temperature, is referred as the primary feedback loop. The primary controller the primary controller used in this loop that compares the set point temperature of the liquid with its actual temperature supplied by the thermal sensor. However, instead of directly positioning the control valve, its output becomes a set point signal for the secondary controller. Because the secondary controller has the capability of receiving its set point from an externally applied source, it is referred as a remote control. In addition to its set point input, it receives a feedback pressure signal from the sensor placed inside a steam chamber going into the heat exchanger. Based on the results, when the comparing the set point and the feedback signal, the inner loop secondary controller positions the final control element. So there are two conditions that will cause the secondary controller to reposition the steam ball. First, if there are any fluctuations in the steam pressure, an error signal develops due to the differences between the changed feedback signal and the stable set point signal. So this result is the valve position changes, which causes the steam pressure going into the heat exchanger to return to the desired level before the temperature of the liquid is sustainably affected. The other condition is that it also causes the secondary controller to adjust the valve if the set point signal it receives from the primary controller wires. If this condition or if this situation occurs, if there's a system set point change made to the primary controller or of the feedback signal from the outer loop varies to the disturbance or load change of the controlled variable temperature. Either situation that creates a new error signal at the primary controller output, so which is fed to the secondary controller as a different set points. So the merits of the Cascade controller, by only using the proportional mode in each control loop, Cascade control often results in faster, more precise performance than with a single loop PID control system. When you're tuning of Cascade control system, always tune the secondary loop first. The proportional band of the secondary loop should always be narrower than the proportional band of the primary loop. To be effective, the time constant of the inner loop should always be there to 10 times faster than the time constant of the outer loop. And next important method is the feed forward control method. So here a liquid passes through the tube section of a heat exchanger which rises its temperature to the required level before it is before it is discharged. So the outflow, which is the control variable, is fed to a mixing tank for future processing. The heating medium is steam, which is passes through the shell of the extension. The steam is the manipulated variable, where the control valve is used as a final control element to vary the flow of steam and therefore the heat that is transferred to the product. The sensor located in the outlet pipe reads the temperature of the control variables. If there is a disturbance causes The outgoing fluid to device from the set point, the controller causes the valve to vary the amount of steam that passes through until the situation is completely corrected. However, while correcting this action taking place, the enormous product is being produced. So the operation of the feed forward control is based on by taking the corrective action. If it is affected by the disturbance, the derivation of the controlled variable from the set point is reduced or eliminated. The next method is nothing but the ratio control. Ensure that your quality product is produced. The quality of each ingredient must be very precise. One method used for mixing application is to proportionally control the flow of one ingredient based on the amount of flow of another ingredient. So this pressure is called as the ratio control. So the figure what is shown over here is a ratio control system. So which has a sensor used to measure the flow of rate of flow, while flow, and another sensor used to measure the flow rate of the control flow. The flow rate of each line is measured by reading the differential pressure across an phrase plate, and which is non-linear. A square root extractor transducer is connected between the DP flow sensor and the controller. So its function is to convert the non-linear output of the pressure sensor to a linear signal that is proportional to the flow rate of the each liquid. By using the flow signal from each line, the controller varies the flow position that adjusts the control flow and maintain it in proper ratio to the while flow. Next, one of the control is the pneumatic controllers. So that produces the pneumatic output signal that is applied to your flow control valve. So usually located in the field that are mounted near the point of measurement. So these controllers are usually found in older system and that are capable of controlling only one loop. So here we find this panel mounted controller is a microprocessor based device which can measure a display, which can measure and it can display and control the temperature, pressure, flow, and other process variables. This device is relatively inexpensive and is capable of performing simple on and off as well as the PID type control applications. So the diagram of this type control is shown here that you can see it where the users can select the instrument functionality reviewed from menus using Excel membranes keys and the high intensive liquid segment display. By pressing the M button, several modes of operation can be accessed such as on-off parameters, PID gain settings, and the present limits and preset the limits that activate an alarm when they are exceeded. The specific value for each mode are shown on the digital display as they are programmed by pressing the up and down arrows after the programming key is pressed. The bar graph is also indicated indicators and on the left display by the set point value selected and a runtime status of the process variable that is being controlled. The tune button is also used for auto tuning, which is automatically selects the gain settings for PID mode. So where R button performs the reset function if the programmer needs to repeat that keypad entries. An auto or manual button also enables the operator to use the controller to either operate in the manual mode or in the automatic mode. So when in the manual mode, the controller function is performed by the user, but in the automatic mode, the control function is performed the microprocessor based circuitry. So in conclusion, we have explored the fundamental concepts of the industrial process control system and their significance in modern automation and manufacturing industries. And we also have discussed the principle of open loop and closed loop control system, and we have analyzed the process behavior and controller operation and examined the various control modes, including on-off, proportional, integral, and derivative control. We also introduced the advanced control strategies such as cascade method, feed forward control method, ratio control method, along with an industrial controllers and instrumentation techniques. Understanding these concepts provides a strong foundation for designing efficient, reliable, and automated industrial process. And thank you for watching this session. So in the next video, we will continue our exploration of process control systems and with more detailed analysis and applications. Thank you.